Another issue with power series is that if we have two series that are equal, can we always say that AN is equal to BN? And you may think that this is kind of a silly issue, but it's actually not as silly as it seems. Because if you have a sum of things equal to another sum of things, then certainly it doesn't mean that the coefficients have to equal. A sum is the combined effect of three things, and it need not be true that AN is equal to BN for all n in general. In our case, in general, these will be equal under some mild assumption. But what we will need is that this is not true for a single x, but for all x in some range. So we'll need true equality for many x. And we'll try to reduce the number of x's that we need. So first, a simple theorem. Suppose you have two power series that are defined on their own radius intervals of convergence. And suppose that they agree on some small interval that's contained in a domain where both of these converge. Then we can conclude that the coefficients are equal. So let's draw a picture of a little bit the domains here. So we have f is converging on some interval. G is converging on another interval, possibly smaller or bigger, but let's draw it like this. And we have the epsilon interval here, centered at 0, is some small interval centered there. So it's all of these expressions are defined because we are in this small interval. We're assuming if the functions equal here, then actually they have to also equal outside the set because the coefficients are the same. Okay. Well, the proof it's quite straightforward and gives us also some new insights. So well, we know that both are smooth by the theorem, so we can differentiate infinitely many times. We also know that the derivatives can be recovered by term-wise differentiation. So we have the formula for the nth derivative. Now, if we plug in 0 into this expression, what happens? And this should be n minus n. Well, almost all of these terms vanish. These terms vanish if n is strictly less than m, because one of these factors will be 0. This term will vanish once n is strictly bigger than m because it contains a factor of x. So the only term here that does not vanish is when n is equal to m. We're left with m, so n is equal to m, so m minus 1 times all the way up to 1 times am. And similarly, if we do it for b, we get that the derivatives, we get the same formula. And because these functions are equal in the neighborhood, the derivatives are equal and the coefficients are the same. As a corollary of this argument, we also get a formula for the coefficients of the power series. If it converges, then how it relates to the derivatives is by these factorial expressions that are familiar from Taylor series. But let's try to weaken this assumption. It turns out that these don't have to agree on an interval. They can agree only along a sequence of points. So let's suppose we have some two power series. They're defined on minus r to r. Let's suppose that they agree along some sequence here drawn in red, xn. So there exists some sequence xn that converges to 0. And by the way, all of these could be x naught, but now in this lecture, I'm going to focus on the 0 case. And xn is not equal to 0, so that the functions are the same on this red set. Then I want to conclude that actually they're the same everywhere, and an and bn are the same. So, proof of this. Let's look at f minus g, fx minus g of x. And let's give this function a name, h of x. So I can always, this is a 131a fact really, I can sum up power series. So h of x will have a power series an minus bn x to the n. Because it's true once these are separated, and you can merge the sums together. Okay, so let's call this Cn, just so we have a name. And what we want to show is that Cn is equal to 0 for all n. Well, let's suppose not. If it were not 0, then there exists some capital N, and we can make it the smallest so that C capital N is not equal to 0, and Ck is equal to 0 for all k less than or equal to n. So we choose the first index here that is not equal to 0. It could be the first index. So n could be equal to 0 even. There's nothing illegal about that. Okay, so let's choose that. So we choose, we don't just say that there exists, but we choose such an n. And let's write this h in a little bit different way. So h of x is equal to sum equals n from capital N off to infinity of an of Cn x to the n. This is because of the vanishing assumption here. We can drop the first terms. They don't give us anything. And then I want to take it a factor. I take it a factor x to the capital N, and I will shift the indices so that they start from 0. So if I want to shift the index, I'll have to place n plus capital N, and then x to the n. So in this process, what I did was I shifted the index n minus n, taking a factor of capital N out. And when I shift the index back by n, I have to add n to get the same indices. So these two series are the same. But this way of looking at this makes this clear. So what we have here, we have a function gx, and this has the same radius of convergence as the original one, because we have only shifted the indices. It's a nice little exercise. So same radius of convergence as h, and therefore also it converges on minus r to r. That's the crucial thing. So what can we now say? Well, g of 0 is equal to Cn, which is not equal to 0. And g is continuous by the theorem above on power series. Since g is continuous, there will exist some m such that once n is bigger than capital M, g of x n minus Cn, which is equal to g of 0, will be less than or equal to absolute value of C capital N over 2. So why is this the case? Remember, we have a sequence of points converging, so the function values along xn converge because it's continuous. So we're using the continuity and the sequential convergence, skipping a few steps. So we have that. But what does this mean? This means that g of xn, absolute value, it's bigger than or equal to absolute value of Cn minus the distance between these two. And well, the distance between them is at most a half of the absolute value of Cn, minus sign there. So this is absolute value of Cn over 2, which is positive. Therefore, g of xn cannot be equal to 0 once n is bigger than or equal to n. This is our assumption constantly for this part. So g of xn is not equal to 0 once you have a large index. But let's look at h of xn now. So if n is bigger than or equal to capital M, on the one hand side, h is equal to 0 by assumption, because it's the difference of m, f, and g. On the other hand, it's equal to x to the n, xn to the n, and gxn. And this is not equal to 0. This is a non-zero number, not equal to 0, because we assumed that xn is not equal to 0. So we get a contradiction. This is not equal to 0, yet it is also equal to 0. So not equal to 0, equal to 0, contradiction. So something's got to give, and what gives is that the fact that there were any indices in part that weren't 0 is not possible.